So we have two fundamental algorithms for traversing graphs: breadth first search, or BFS, and depth first search, or DFS. And I've reproduced their algorithms here. One thing I want to emphasize now that they're side by side is that they should look almost identical. The only difference is that in BFS, we use a queue to keep track of our nodes that we have to visit, versus in DFS, depth first search, we use a stack to keep track of the nodes that we have to visit. Oops, this is queue and stack. So it's actually the exact same algorithm, except we use a queue versus a stack to keep track of our current nodes. Okay, so let's actually think about the time complexity of these two algorithms. So I'll go over BFS first. So starting with an empty queue, we add the starting node to that queue. Adding to an empty queue is just constant time. Okay, so while the queue is not empty, so before we do the while loop as a whole, let's just do its contents and then let's figure it out overall. So we pop the current element from the queue. So popping, if I have, let's actually put some definitions. Let's say that V is the set of all my vertices, so magnitude of V is the number of nodes or number of vertices. And let's say that E is the set of all edges, so the magnitude of E is the number of edges for both examples, not just for BFS. Okay, so in the worst case, popping off one element from a queue, well, a queue is always constant time. I can add or remove to the front or the back in constant time if I implement my queue using a linked list. So this is just constant time. If the current node has not been visited, that check is constant time. I just look up a Boolean, mark it as visited. So that's just an assignment. That's constant time for each of its outgoing edges. Well, I could theoretically have a network where my current node has all of the edges in my graph as its outgoing edges. So technically speaking, this step might have to iterate over every single edge in my graph. If the current if the neighbor has not been visited, potentially add it to the queue. This is also constant time. So we have this big O of E term, and theoretically we might have to iterate over the queue big O of E times, but the overall time complexity, despite what you might naively think, it's not actually big O of E squared. Note that no matter what the structure of my graph is, so regardless of if I have all of my edges coming out of one node, or all of my edges, or all my nodes having exactly one edge, regardless of the structure, I only add each edge to my queue exactly once. So I only operate on every single edge exactly once. So in reality, this entire while loop, including all of its contents, is just big O of E. I might have to do some constant time operation for each of my big O of E elements. In reality, there's usually a first step before I even do my breadth first search, which is initialize my vertices. So for example, if I want to find the shortest path between my start node and any other vertex, I might have to initialize some previous pointer, for example, to keep track of what node was the one before me. In general, I might have to initialize something for each of my vertices, which would be big O of V. So generally speaking, if I include any graph initialization and I have my BFS traversal, the overall algorithm of BFS is big O of V for the initialization plus E for the actual graph traversal. the actual BFS. Similarly, for DFS, I would probably have some initialize the vertices step. So initialize all my nodes. This says vertices here. And notice that the algorithm is identical, except instead of using a queue, I'm using a stack. Well, remember, if I use a linked list to implement my queue versus a linked list to implement my stack, in both scenarios, I have constant time access to the front or the back, which means that I have the exact same time complexity as BFS. It's actually the exact same algorithm, except I'm changing the order in which I'm iterating over my nodes. And as a result, the paths that I traverse look different. So because it's the exact same algorithm with the exception of swapping out the data structure, but the data structure has the exact same worst case time complexity, DFS is also big O of V to initialize my vertices plus E, because I have to theoretically do a constant time operation for each of my big O of E edges.